So what would you guys like to go over?
Um, I had a few questions, but first things first, can you please post the solutions to, because I tried to answer the review myself, and I just want to compare it with the actual solutions, just to check everything.
Okay.
Um, if you can upload the solutions, if you have them, that would be good, because I don't want us to like start solving them here, and in that case, we'll be wasting a lot of time of, other students asking questions. So if you can just upload it and then I can review it over the weekend, that would be good. Um,
Yeah, let's see what happens. If people have lots of questions, then the review can go in that direction. But I could also just do some of the problems from the review if you want.
um, maybe. I didn't have problems with it's just the proving ones.
Yeah.
Yeah, that's the only that's the only material I'm a little bit afraid of. So let's just I don't know. If anybody else agrees, we can go over some proof examples.
Yeah, I mean this is for you guys, like whatever you guys want to go over.
I mean, okay, nobody else is talking, so I
Yeah,
guess
proofs are a good idea.
proofs are a good idea.
Okay, but do you have any particular one? I mean, you want
Not
me to?
really. I mean, I don't know how do you make him, but I think the ones in the review would be nice to solve first.
Okay, we can do that.
Mhm.
Let's check those out. So,
Also, one question. In the
uh-huh.
exam, are you gonna tell us to find if it's true or false, or you already give us if it's true or false, and we have to prove it?
It's so the format of the test is there's going to be five problems total. The
Uh-huh.
last two problems are the proof problems, and each one of those will have two parts. The first one will be to prove truth, two things are false. So to answer your question, I'll be telling you that they're false. And the last question will be to prove two things are true. I think that's the order that I put them in. But that's what you're going to have. So a total of four proofs, two prove false, two prove true.
hmm And also, can you go over the essential theorems, or I think you already told us, but like essential theorems for proving stuff, or just the what they call it, sentencing when we are trying to prove something false or right, other than the
Yeah.
counterexample finding.
Yeah. I mean, the main thing is, well, yeah, I mean, we can look at them. Um, okay. Let me share my screen with you. Find that and let me just turn this thing off. It keeps beeping. Oh, okay. Let's see. Which one should we do? Um, I'll go in reverse order. I'll start with number 8 on the review. It says prove the following statement is false using a counterexample. Do you all have access or can you look at the review while we're doing this? So that I don't have to write it out again, the actual question.
Review on
Yeah.
XYZ.
No,
Yeah,
no, the review that's on Canvas.
yeah, just look it up on my
Yes.
phone.
Yeah, so if you could have that in front of you, then I won't have to write out the whole thing again. So number 8 says, prove the following statement is false using a counterexample. If u, v, and w are non-zero vectors in R2, then w must be a linear combination of u and v. Okay, so they're non-zero vectors in R2. W must be a linear combination of u and v. So anytime you're trying to find a counterexample, the first thing is to try to think of the counterexample. So I don't know if it helps to just sort of visualize something. These are in R2. So how could I draw two vectors in R2? Here's two vectors in R2. And there's three vectors in R2. So if u, v, and w, then w must be a linear combination of, let's say this is u and v. And this is
Okay.
w, and this is w. So this is saying that w must be a linear combination of u and v. Now, keep in mind, though, that I just drew this picture sort of at random, and finding the counterexample may involve drawing them in a slightly different way. So you're trying to find something that makes it false. So is there any way you could alter this picture so that there's no way it would be true, the way I drew it?
You mean if one, okay, none of them can be zero, so
Yeah, they can't be zero.
Um, if U and V were parallel?
Yes, that's the idea. So if this is U and this is V, then there's no way that W can be a linear combination of U and V, because if they're parallel, meaning they're on the same line, then any linear combination of them is going to remain on that line. So that's the first step, thinking about it and trying to find the counterexample. Now, I still don't have a counterexample, but once I understand it with the picture, then I can choose the counterexample. So what could I let, let's say, what could I let U be? I'll write it down here. Yeah, I could pick anything, really. But you pick something. Someone pick something.
we want the U 1 1. That would be easy.
Okay, 1 1. Sounds good. So then if we pick U to be 1 1 and we want V to be on the same line, then what's a candidate for V?
2 2.
2 2. Just multiply it by any scalar and you have another vector that's on the same line. Now, all we have to do to get a good counterexample is pick something for W that's not on the line.
Just 5 3. Let's go easier. 3 1. No, that doesn't work. Yeah, 3 1 would work actually.
Oh, they're both good. 3 1. Anything. As long as it's not a multiple of 1 1, you're fine. So now we have our counterexample. We thought through it. We have the counterexample. And now we're ready to write the proof. By the way, while I'm thinking about it, I hope I didn't scare you too much by saying there's 4 proofs. I did devalue them a little bit. So those 2 problems are worth 10 points each out of 100. So you only have 20% of the test being on the proofs. So if you can do all the computational stuff, then that's 80% of the test.
Mm-hmm.
Okay, so anyway, proof. So I'm going to start my proof. So the little thing that I said that might help you to remember is let, then, but. So when I mean let, I'm going to just state my counterexample. Let W equal 3 1, U equal 1, 1. And V equal 2, 2. So that's the let part. I'm just going to find my counterexample, then I'm going to state it, let whatever it is, my counterexample. Okay, then the second part is I want to show that the hypothesis is satisfied. Now, what's the hypothesis? If you go back and look at it,
Non-zero vectors in R2.
yes, good. So we just want to note that the hypothesis is satisfied. Then W, U, and V are non-zero vectors in R2. And finally, but now this is where I want to show. So the first part is counterexample, then show the hypothesis is satisfied, and but now show that the conclusion is false.
We have to compute it.
Well, here's the thing. If you have a valid counterexample, you really don't need to show much. I mean, like if I look at this and you give me this counterexample, it's clear to me that W is not a linear combination of U and V. So really, at a minimum, you could get away with just saying it. But, oops, let it go. But W is not a linear combination of V and W.
So we don't have to prove this like by computing it, right?
Well, the counterexample is the proof.
Okay.
Now, there's sometimes a gray area in proofs, like how much do you need to show? How clear?
Exactly.
And yeah, that's one of the hard things. But if you come up with this counterexample on a test, it's like you couldn't have found this if you didn't understand it. So you're not going to come up with a counterexample just guessing at vectors. Well, you could get lucky, I guess. But if I saw this, I would have no problem saying, okay, this is right. W is not a linear combination of U and V. And then therefore the statement is false.
We don't lose
What was-
points if we try to over-explain this, right?
No, sure, absolutely not. Like if you were to, if you were to draw a picture, like we have the picture up above, or if you were to say something like, notice that U and V are on the same line, but W is not, something like that. You could say that would just provide even more clarity.
Or if you could say W equals to RU plus RV, but SV, but R and S doesn't exist. They don't exist.
Yes, and that's fine, but that's really just the same thing as saying that W is not a linear combination of U and V.
Yeah,
It wouldn't provide any more clarity unless you actually turned it into a system of equations and found that it had no solution. Now that would really make it clear. If you wrote that linear combination, turned it into a system of equations, did a matrix, and then saw that you got a contradiction, yeah, then that would be even better.
Could you repeat oh, sorry, finish.
Go ahead.
I was just gonna ask, what was the original statement?
Of the proof?
Yeah, of the question.
The question was, if the hypothesis was if u, v, and w are non-zero vectors in R2, then w must be a linear combination of u and v.
Professor, I also have a question about what explanations can be used except the theorems. For example, there's so many things we know about like this, but we just said it in a class. If they're not like a part of theorem. For example, if you give me a proof and I have to prove it false or true, and then I use something like, some explanation that we had written in our like notebook that this is a homogeneous like system and homogeneous system like with less unknowns and equations, something like that, even though it's not a theorem for itself, but we just wrote it down. Can we use that for to prove something?
Well, generally when you write a proof, you want to only use things, either definitions or things that are written as theorems. Now, sometimes, of course, I don't expect you to, memorize. I don't even number the theorems, so I wouldn't expect you to memorize them, even if I did. So you can, if you believe it's a theorem, you can just say by theorem. Of course, it should be a theorem that we've written down as a theorem. Now, I might not be that picky about it, depending on what it is. I mean, like like some of these things, like you said, we've just talked about them a lot. And sometimes I've written them down as theorems, sometimes not, some things. But so, if you can't cite a theorem, then just go ahead and give an explanation that you think is valid based on what we've talked about. Now, what you don't want to do, though, is bring in something from another book that maybe we haven't even talked about yet. We want it to be only based on things that we've talked about in the class,
Hmm.
that we've written down or proved.
Okay, understood.
Okay. So, Howard, any questions on that one? Okay. So I did say, like two of the, I said this in class and I'll repeat it now. Two of the main definitions that we've had so far, the main concepts in linear algebra, are the concepts of linear combinations and the concept of linear transformations. So I'm certainly going to involve a couple or maybe even all. I don't even remember what I put now. the ones I put, but those are the main ones that I want you to know. So in terms of definitions, you must know the definition of linear combination. You must know the definition of linear transformation. Okay, let's look at let's do number 6, because this is one that's not true. So this is I'll write down the transformation. T is a mapping from R
Up
or
to 7? Are we skipping that?
No, I'm just
Okay.
since you didn't request any particular order, I was just
Oh,
going.
okay. So just the order. Okay, okay, got
Yeah,
it.
do you want me to do 7 instead? That's fine.
If we can go in the same order, like, yeah, from the end to the number 5, that would be good.
Okay, just go backwards. Okay.
Yeah, yeah. Thank you.
Okay, so 7 says prove that A is the inverse of B and use the definition.
What's the definition to 1 over a d minus bc or
So that's the thing is that's the formula. So that's what you just asked is a really good question. Because the formula is different from the definition. The formula that we have is only for a 2x2 matrix
oh,
and doesn't work for any other size of matrix. So that's not the definition. That's just a formula that happens to work for 2x2.
uh-huh. Okay.
So what is the definition? What makes two matrices inverses of each other? by definition?
If we multiply them, we get the identity matrix.
That's it. That's it. That's the definition. A,
Coordinate.
your inverses. I'll just write, before I do the proof, I'll just write it down. A and B are inverses. IFF, that means if and only if. A times B is equal to the identity, and B times A is equal to the identity. That's the definition. So to do this proof, and it specifies, use the definition. But that was really a good question, because I'm sure a lot of people maybe tend to remember formulas more and would just use the formula on A and find that you get B. Okay, so proof for, and that you wouldn't have to rewrite this because this would be written on your paper, but I'm just going to jot it down here. So for A equal 2168 and B equals 0.8, negative 0.1, negative 0.6, and 0.2, comma. Notice how I'm always trying to, when I write these proofs, I'm always trying to make it something that I could read, like I could read out loud to myself as a paragraph. Let's just go back up for a second to this other one. See, notice how I can read this. Let W equal 3, 1, U equal 1, 1, and V equal 2, 2. End of sentence. Then W, U, and V are non-zero vectors in R2. Another sentence. But W is not a linear combination of U and V, and another sentence. Therefore, the statement is false. So just as a guideline, when you're trying to practice these, if you can't do that, if you can't like literally read your proof, it's probably not right. You probably need to add some wording into it to make it read, because it's, remember, at its essence, a proof is an argument. It's an explanation of why something is either true or false. So it needs some kind of language attached to it.
Mm-hmm.
Okay, so AB.
Professor, one question. Can we just prove this by finding the inverse of A and saying that either it doesn't equal or equals to B? So
No, that's what is, who suggested that we use the formula first?
oh yeah, that was me too. Okay.
That was you, right? I thought so.
Yeah.
That's the point. That's, if you did that, that's not the definition.
Oh, okay. That would be like more proving it false, right? Or still not.
No, well, not using the definition. See, that's why I specified on this problem, use the definition.
Okay.
Because for a lot of stuff, you have, this is the way math evolves. You make a definition, and then using the definition, you prove other things.
Mm.
And those are theorems. And then once you have a theorem, now you can use that theorem to prove something else. And then maybe you add some more definitions. And then from that, you prove more theorems. So there's always the definition, knowing what the definition is. That's like the origin of everything. That's important. So if I don't specify that, if I don't say use the definition,
Mm-hmm.
I couldn't, I mean, I would have a hard time counting it wrong if you just used the formula and got the right answer. But what I wanted to, if I was to give you this problem, it would be for me to see if you know the definition. Because this will be a definition we use throughout the course. There's a lot of things that are inverses of each other, and the way that you prove it is well, if they're matrices, you multiply them together and you see if you get the identity.
Yeah.
Okay, so 0.8 minus 0.1, minus 0.6, and 0.2. Now, if this was on a test, why would I be justified in just writing this without even thinking about whether it's actually right or not? This is I'm don't expect you to think in this way, but if I'm telling you that it's true, then this has to work. And you know the definition, this has to work. Either that or I made a bad problem, which I hope I didn't. I mean, but we could certainly check it, check a couple of them. 2 times 0.8 is 1.6, and then
That's
minus.
correct.
Okay. So you checked it.
Yep.
Okay. And then we'll put an and here, just like to keep the sentence structure going. And then BA is equal to 0.8, negative 0.1, negative 0.6, 0.2. And that's equal to 1, 0. The identity also. Oops, I didn't do the other one. Times 2168. Okay, and there we go. That's all I needed. Therefore, A and B. Oh, it says A is the inverse of B. So I'll just say therefore A equals B inverse. I could have also said A and B are inverses of each other. Or I could have written it in words. A is the inverse of B. I just wrote it symbolically. Okay. Okay.
So why didn't you actually did you do the calculations, or did you just write out that it equals the identity for each one? Or did you do it in your head?
You can do it in your head.
So my logic was that, okay, I'm taking this test. I've been told that it's true.
Okay. It's saying prove that this is true.
Right. It's saying prove this is true.
Okay.
So I know it has to be true. So that means those have to be true. Now, I started to check it and then even said that he had checked it. So, but yeah, I mean, you could certainly check it. It's not a bad idea. But, little things like this, if you're nervous, if this is a problem on a test and you're nervous and you feel like you're running out of time or something, you might not want to take the time to check every single thing. The main thing is, do you know the definition?
Right. Okay.
Okay. So going backwards, number 6. So here we have T is a mapping from R to R, and it's given by T of X equals 4x plus 3. Prove that it's not a linear transformation. And then it gives you a specific direction. It doesn't, instead of saying find a counterexample, it says use the definition of linear transformation to show that it does not preserve either addition or scalar multiplication. Now, I was wondering if that wording was clear or not, but what it's supposed to mean is that you don't have to prove both of them. If you're showing that a transformation is not linear, you do not have to verify that both equations are false, only one of them.
Mm-hmm.
So let's, what is when I say does not preserve addition? So what does that mean? The preservation of addition is defined by this equation. T of x plus y equals T of x plus T of y. if you can verify that equation, then you're halfway home to proving that it's linear. If you can prove that that equation is not always true, then you're all the way home on proving it's false. And that's what we're trying to do here, is prove it's false. So now sometimes one of them is true and the other one is false. And sometimes both of them are false when it's not linear. So I can try working with this one first of all, and if it doesn't work, then I'll if it happens to work, maybe it is true, then I could try the other one. Okay, so so let's try. Let's start the proof. Now, notice this is a little different because I've kind of suggested a way to do it, because I mean, I could go for a specific counterexample, but this will kind of do it, and I'll show you how to address that. When we're talking about a linear transformation, we want to make sure it says t of x equals 4x plus 3, but the equation is t of x plus y. So we want to take a second to say what the x and the y are, and those are just going to be elements of the domain. So we're just going to say let x and y be in R. So that means they're in the domain. Now, if I was going to prove this, I would also say, and let R be in R, because I would need a scalar to prove the second property. Then,
Okay.
go ahead.
Nothing.
You're good. Okay.
Yeah.
Okay, then let's go. Let's do this the easy way. Let's do t of x plus y. And we'll work this out first, and then we'll work out the other side second. So what is t of x plus y?
4x plus 4y plus 3.
That's right. So the rule here up above, whatever you put in there as the argument of t, that goes in here. So if I put in x plus y, then it's 4 times x plus y plus 3. And then, as you said, that's equal to 4x plus 4y plus 3. So, notice it's starting to take the structure of a counterexample proof. I just stated the things that I'm going to work with. It's not a counterexample, but these are the objects that I'm going to be using, x and y. Then, so if you think of the other side of the equation as the conclusion, if t of x plus y equals 4x plus 4y plus 3, then t of x plus t of y should equal that also. So I'm gonna say, but
Could we do that first and then say, but it doesn't preserve addition?
well, I can't assert that until I see this side. This is just the result of t of x plus y.
No. We write this down in this part, but we don't say but here. You know what I mean? Like we just write that down and say they don't equal to each other, but t doesn't preserve addition, something like that.
Sure. So we could also say and t of x plus t of y, if you want to do it like that, equals, so t of x, the rule says it's 4x plus 3.
Plus 4y plus 3.
And the rule says if we plug in y, then it's 4y plus 3. but that's equal to 4x plus 4y plus 6. So the point is, they're not equal. One has a 3, one has a 6. And, even though x and y are not specific numbers, it's very clear that these are not the same thing. I mean, there's no way that these can ever be the same. You can't choose values for x and y. Since the 4x and the 4y part are the same, you can't choose values for x and y that would make them the same. So there's no problem here, just saying, therefore, t of x plus y is not equal to t of x plus t of y. And this is really enough. You could also say it does not preserve addition, but really this is better. That's what this equation shows. It shows that it doesn't preserve addition. But in terms of doing the proof, this is what you want to do. You want to just show that the two sides are not equal to each other. Therefore, t of x is not equal to t of x plus t of y, and therefore t is not linear. If you also want to say, therefore, it doesn't preserve addition in the middle there, that would be provide even more clarity.
What would that make t? Or if it's not a linear transformation, then what is it?
It's just a function. It's a function that maps a real number to a real number, but it's not a linear function.
Oh, okay. Not linear function.
Yeah. And notice how different this is from, and all throughout algebra, pre-calculus, and calculus, this would be a linear function. So we're looking at this in a different context now. We're looking at R as R. Yes, it is the set of real numbers, but we're looking at it really as a vector space now. And the definition of linear transformation is a vector space definition, a mapping from one vector space to another.
And this is preserving the same vector space. It's not changing.
Well, in this case, the codomain is the same as the domain. It's a little, when I say it preserves addition, that's kind of an unclear term, and different books have different ways of describing that. It's just, we want to have a way of describing this equation. So preserves addition just means that you can add the vectors together and then apply the transformation, or you can apply the transformation first and then add together, and you'll get the same answer either way. All preservation of addition means is that this equation is true. Now, some books say it respects addition. I don't know if that's any clearer. But I like preserves. But, it's not even 100% necessary to say that. So notice just one thing about the definition again. I've said this a couple times in class, but I'll say it again. We have this theorem that once we have the definition of a linear transformation, we have this theorem that says if you have a matrix transformation, it's automatically linear. So since we had that theorem, you could cite that if you had the matrix of the transformation. But I'm here I'm specifying, use the definition. So the definition involves those two equations that describe the preservation of addition and scalar multiplication.
Can we move on to another problem?
Yep.
Can you do 1C, please?
What is that?
Oh, 1C. 1C. You want to do 1C without doing the rest of 1?
Yeah.
Well, the trick to doing the trick, let's do problem number 1.
Oh,
The trick to there's a not a trick, there's a concept involving doing part C. And in order to see what the concept is, you have to do part A and B first. Well, you have to do part B first.
yeah, finding M and N actually, that would be nice to do.
Okay. 1, 2, 3. 2, 5, 4. 3, 7, 7. And 1, 1, 1. So you're given this matrix. This is matrix A. And then you're given a T. T is a transformation. It goes from Rm to Rn. And the rule for T is that T of a vector X is just equal to the matrix A times X. So this is a matrix transformation. Now, the key to answering part A, what is M and M? So M is the dimension of the domain. So if it was R4, that means that our inputs would have to have a dimension of 4 components. So this question really amounts to testing what would the length of the input have to be if we're doing multiplication. See, we're going to put, if we choose a column vector, we're going to put it right there next to A and multiply.
Yeah.
And so the idea is A is 4 by 3. So what would the vector have to be?
3. 3 by 1.
3 by 1. It's going to be by 1 because it's a vector. It's not a whole matrix. But the point is those have to match in order for the multiplication to be defined. So M is equal to 3.
Mm-hmm.
Okay, and then now what's the output?
That
So
would be 4 by 1.
that would be 4 by 1. So remember this little trick. Those have to match for the multiplication to be defined, but the size of the output is the outer two numbers, 4 by 1.
We only count the rows, right? For N, that would be 4.
What do you mean?
So the output is 4 by 1,
Yes.
and how do we say the N?
Well, so 4 by 1 means that it's a column vector with 4 components.
Uh-huh.
So that's in R4.
Okay.
That's the output. So M equals 3, and N, that's the dimension of the codomain, which is where the outputs live. That's 4.
Mm-hmm. Professor, for problem C and D, do we have to put the matrix and then equal it to that specific like matrix that are provided every time, and reduce relational format to find if it's linear combination? Or
That's a great question. But let's go through it so that we see sometimes you do, sometimes you don't. Depends on how the problem is written. And there's a certain logic to the way that these part A, B, and C are connected. So let's see. So in part B, X is given to be -1, 1, 2.
mm-hmm.
And it's just saying find T of X. So T of X by definition above is just
A
the
of X.
a times x. So let's write it down. 1, 2, 3, 2, 5, 4, 3, 7, 7, 1, 1, 1. And we're going to multiply that by negative 1, 1, 2. Okay, so we have to do 4 dot products. So we have 2 plus 6 minus 1. Wait. 2 plus 6 is 8, minus 1 is 7. Let's see, we have 5 plus 8, 17 minus 2. Wait a second.
What happened?
5 plus 8, 13. 13 minus 2 is 11. Okay, sorry about that. And then 3, 7, 7, that's 7. 21 minus 3 is 18. And 1, 1, 1. So negative 1 plus 1 plus 2 is 2. That's all they're asking for in part B.
Wasn't part B? Oh, yeah. Okay.
Okay, now someone asked for part C. So you have to make a couple of very important observations here. Notice that in part C, it says write 7, 11, 18, 2 as a linear combination of, 3 vectors. Those 3 vectors are the columns of matrix A. And notice that 7, 11, 18, 2 is the answer that you just got from part B. So if you understand the concept here, you may not see it clearly right now, but I want to make sure that you do see it after we're finished. This is a really easy problem.
I mean, we just, yeah, doing the same thing, but we have to find what they call it, the scalars.
What I'm claiming is there's absolutely no work to do for this.
Oh, okay. Oh, we already have the, yeah, we
I'll say
already have the
stop.
scalars by minus 1, 1, 2, huh?
Okay. So here, let me write it out, the idea, so you won't just have to visualize it. 3, 7, 7, 1, 1, 1.
1, 2, 3.
So we learned that for this type of matrix multiplication, this is the matrix, well, we called it the matrix form when it was related to a system of equations, but we learned that you can do this multiplication in a different way. You can take the first number in the column vector, multiply it by the first column,
Mm-hmm.
and then plus 1 times the second column, 2, 5. Oops, my pen is glitching. It won't write for a second. What's happening to it?
I think it's your internet.
No, it's just gets glitchy sometimes. I just have to like
Because your video and your audio got
I
glitchy too.
can't.
It's like your audio got glitchy too. It's,
Oh, is my voice glitchy?
yeah. It's got a delay
Oh,
too.
okay. Oh, okay. So maybe that is the internet. But yeah, but this is not working at all. Let me just what do we do here? It's not my screen is totally unresponsive right now. Usually I can find a fix for this, but we'll see. Ah,
Maybe you can try turning off the screen, turning it on back. I don't think that helps, but maybe it does.
Yeah, you guys are, your voice is breaking up for me now too.
Oh.
It's saying low system may affect your audio quality. If I do what? Stop my camera. Let's see, I can't even do that though. Okay, that's responding now. It's just some reason it just got really slow all of a sudden.
Does your device have enough battery? Could be.
Yeah, no, I'm plugged in. I'm plugged in. My battery seems to be high, full. Let's see. Oh, I think I shut the video off.
Oh yeah, your voice got a little better right now.
Okay, good. And that was a good suggestion. And my pen's writing again too. Okay, so back to this 1 times 2, 5, 7, 1, and then plus 2 times 3, 4, 7, 1. Now, you don't need to write this out, but you need to understand that the equality between these two things. Because if you write it this way on the right side, what is that? Well, we already know that from part B that the answer to this matrix multiplication is 7, 11, 18, 2. Well, what was the question? The question was write 7, 11, 18, 2 as a linear combination of those column vectors. Well, that's exactly what that equation is telling you. Is that making sense?
Yeah.
I really like this kind of problem. I love problems that there's just a concept. If you understand the concept, there's no work to do. You just write it out. So that's the answer. The question was to write 7, 11, 18, 2. Now, someone asked, well, do we have to do RREF or something like that every single time? Well, obviously, in this case, you don't. Now, if the answer for part B hadn't come out to be 7, 11, 18, 2, it would have been a different story.
Which is the part D, right?
Which is part D, yes. Okay, so let's do part D.
Yeah, I made a mistake solving C first, so so I had to go through all of that again.
Yeah, I'll say when you're doing these computational problems and you're trying to find the RREF, really take your time and try to double check as much as you can, because it screws everything else up if you get your RREF wrong.
Yeah.
Now, what's the quickest way to do this part D?
Well, you just write the matrix A we had and equal it to the vector we have, and then solve for REF.
Yes. Yes. I'm not sure if that's clear to everyone. That is what you do. Let me just write this out just to show you why that's the easiest thing to do. So if we were to do this from scratch, we would say, okay, I need to find scalars x1 times the first vector, 1, 2, 3, 1, plus x2 times the vector 2, 5, 7, 1 plus the scalar x3 times 3, 4, 7, 1 such that that's equal to 0, 0, 0, 2. I mean, so that's the definition of linear combination. If I can find those scalars, x1, x2, and x3, then the answer is yes. And, it says justify your answer. Well, to justify your answer, the best way to answer it would be to just actually produce the linear combination that works. But here again, notice on the left side, we're going to use this equivalence between matrix multiplication, this time to go the other way. That left side is equal to the matrix, so columns 1, 2, 3, 1, 2, 5, 7, 1, 3, 4, 7, 1, times x1, x2, x3. And that should be equal to 0, 0, 0, 2. So when I write it this way, now I could actually go one step further and write the left side out as a system of equations. 1x1 plus 2x2 plus 3x3 equals 0, etc. But I don't need to. We already know that if we have a system of equations in this matrix form, the way that we solve it is we just form the augmented matrix 1, 2, 3, 1, 2, 5, 7, 1, 3, 4, 7, 1, and then we augment with 0, 0, 0, 2. This was our process. So I just want it to be really clear to everyone why you're essentially just taking those three columns of the matrix, augmenting with the vector that you're trying to express as a linear combination of the other three. So it goes from definition of linear combination, using the equivalence of the matrix multiplication to clearly see that it's just a system of equations. Okay, so now we have to do RF. So the problems here are a little out of order. If I was being a little more connecting things a little better, I would have made find RF. Oh, now I see what I was saying. So it may be possible. Notice that this question, part D, it doesn't say express 0, 0, 2 as a linear combination of the other three. It just says, is it? So it may be possible to not find RF, not to go all the way and get the answer. Let's see. Okay, so I'm not going to write down the equations unless you want me to. Tell me if you want me to. I'm going to do the normal thing. So I'm going to zero out underneath this first leading one. So I'm going to multiply the first row by -2 and add. So I'll get 0, -4 plus 5 is 1, -6 plus 4 is -2, and then 0.
This gets fractional actually, but it works.
Okay. Multiply the top row by -3 for the third row, get 0. -6 plus 7 is 1. -9 plus 7 is -2, and 0.
Again.
So that kind of shows me I might be on the right track because I'm getting two rows that are the same.
And we can get rid of one of them. Something happened to the professor, or is it me?
No, you're right.
Oh, thought I disconnected for a sec. Think he was having the Wi-Fi issue.
Yeah, it's weird that the Wi-Fi affects his pen.
No, Wi-Fi affects his connection and then his
There
Probably
you
his
go.
because
bugs.
it's with my
I could see the the
One node.
antenna of his Wi-Fi at the bottom of the page going up and down.
Mhm.
Maybe he was sitting too far from it, I guess.
sitting too far from Wi-Fi.
Yeah, like, from the router. Could be. Because the signal was getting like from jumping to 4 to 3.
Uh, we can continue.
Yes, I actually solved that this D part. It is a linear combination, but man, it was long, like, and it gets fractional at some point.
Lance, can you share your screen or can you? Has he
Oh,
died?
Yeah, I have I'm host now, so
You're the host,
if
yeah. Can
if
you
there's
turn
anything
on
you want to
share
see, yeah, do you want me to share the review?
or enable share screen? Because I can
Oh,
share
yeah.
my screen.
I think we
It's-
can already, no? Oh,
Oh,
host disabled? No, we
Yeah,
can't.
yeah.
Let me see.
I don't know how you do it, but he'll probably be back soon. But just in case.
That's kind of weird though.
I think you should be able
Totally
to.
disconnected. I mean, I was not expecting that.
Yeah.
Dude,
Yeah,
what
try
if it
sharing
was
your screen.
powered?
I think I
Okay.
enabled it.
Yeah, I can do it. Can you
Alright,
guys
cool.
see this?
Yeah.
Oh yeah.
Okay, did I do this right? The fourth row? They're all the same? Or except the negative
Wait a
one?
second. No, you did the last one has to be 1112. Oh, wait a second.
Oh.
How did you get that?
I did it all in one
Okay,
operation.
let me see.
Because I did this fast while he was talking, so I wasn't really focused.
Okay, yeah, so one of them removes and yeah, 0, 1 minus 0, 1, 2 minus 2. Okay, that is correct. And then 0 minus 2, 0. I think that's right.
Okay. Then
Right track still, but you might yeah,
let me
you
just
might need to multiply the last row by -1 just to get it as 1, 2.
do next we'll get rid of we have the leading one. We need to get rid of this, and this.
I mean, you can just no, you can add you know, the second
Mhm.
minus second row to the third row, and then you get rid of one of the rows.
Okay.
Or
So
sorry, it was a different thing. Wait,
or the third row equals the second row plus the third row.
second row plus no, no, no. Negative that, I guess. Negative second row plus third row. Because you want to get rid of it, right? Both of them are 1. You want
One
to,
negative 2.
yeah.
So that would get rid of it, right? Get rid of third row.
No, I mean like you're just adding them.
No, I have yeah. I
Oh,
have
yeah, I have the -1. Okay, I can't see
yeah.
it. Yeah,
So
make it 0, 0, 0. Yep.
that. Is there
Okay.
anything else we can add? Or
Okay, now what you can do is minus C plus. That's what I have, but it's a different one.
row 2 plus row 4.
Or
0,
yeah,
negative
okay.
4.
Okay. Now you can just simplify the last row into -1, or just make it 1,
Hmm.
-1 over half. 1/2, -1/2.
Oh, we would want it to be 1.
Exactly, right? So we can just simplify
Yeah.
it. Just say 1 and negative 1/2.
Yeah. Hidden row.
Nice. You still have 1 through 3 in the beginning? Okay.
We have to get rid of, yeah. Because
Okay.
I do column by column.
That's okay. Just -2 row through plus plus just row 1, I guess, just to get rid of 2.
Yeah.
Or you could get rid of the -2 in the second row first by using the last row, and then do operations
Yeah.
on the first row just to,
No, I see the way you're thinking. So out of my order, but that actually saves time.
maybe. So 0, 1, 0, -1.
Yeah. Yeah. And then we can, okay, perfect.
Oh, you missed the 1.
Oh, where'd it go? Row 1 equals -2 row 2 plus row 1.
Also -3 row 3. No, you don't have to copy it. You can do it at the.
Oh, in the same,
I mean the operation just, not the. Oh, you don't have space? Okay.
yeah, never do.
Make everything smaller.
Yeah, I was thinking about that.
Bring it up. Pick it up. Oh, okay. That fits. That fits.
Okay, I'll make this smaller.
No, I used a different paper because it wasn't enough space.
I would use the other
Oh,
page.
you have, you have enough space. We are almost done, so we
Oh,
don't need
okay.
it. Yeah. Okay, so you want to also say R1 equals -3R3 plus R1
On the same one.
on the same one. I mean,
Are we able to do
you
that?
do the first one. Um, I guess you do the first one and then you do the second one. I mean, maybe don't do it.
I'll
Yeah,
just
just to be
take
safe.
the longer route, yeah. Okay, so that means that this goes to 0 and
That
this,
becomes 2.
yeah. Okay,
He might have had a power outage because it took him a long time. Um,
yeah. Now it's just
so
3.
yeah, so you know, -3 last row plus first row. I don't know why you guys, especially Professor, uses R4, R1 because I use ABC, you know. I
Yeah.
just name it. It's so easier because then you have to write R every time.
Yeah, I don't mind it just because it looks pleasing to me.
Yeah, same.
Okay, what did I do? R3 or R4, -3, so that's 0. And this times -3.
-3/2 plus 2.
3/2 plus 2 is 4/2, so 7/2.
Yeah, that's it.
So then
7/2 multiplied by the first vector plus -1, second vector -1/2, third vector, I guess.
wait. Yeah, X3. Is that
This one is the scalars, but
yeah, those
Can
are
you
the,
hear me?
what's that?
Can you guys hear me? I got back on.
Yeah, hi.
oh yeah, hi Professor.
Sorry about that. My computer completely crashed, and then when it came back on, it decided it needed updates.
Oh,
That's great.
oh, that must have been why, because Windows automatically downloads the updates and then restarts.
That's crazy.
Yeah, yeah. I have this. You just have to turn the like automatic updates off sometimes.
Oh,
First, your internet got slow because it was downloading, and then it restarted to update it.
yeah, yeah, yeah. Okay.
We
Well,
finished the RF.
oh, you did?
Yeah.
Okay. Let me share my screen with you again and oh wait, I already I guess it was already sharing.
No,
No, no.
No. Oh, it's
now
not
it's
sharing?
sharing. Now it's
Now
sharing.
it's
Yeah.
I shared
Okay.
my screen and we did it.
Okay. All right. Let me see if I can get back to where I was. Is this where we were? Yeah, this
Yeah.
is where.
Yeah.
Okay. So, good. You got the RF. I wanted to show you though something where it may be possible to answer the question before you get to the RF.
Mm.
Let's look at that. So, let me just finish this off. So we're multiplying by -1 and adding -1, -2, and 2. Okay, and 1, 2, 3, 0. I don't know if you guys did it the same way. I'm going to do it. So I'm going to just do some shortcuts here. This row is the same as the second row, so I'm going to be able to zero that out. I'm just going to put that at the bottom. So that one's gone. I'm going to keep this second one the same. 1, 2, -1, 0, and I'm going to move the I'm going to add the second one to the fourth one here, and then add that answer to the third row. So I'm going to get 0, 0, -4, and 2. Now, if you look at this matrix, I claim that you can answer the question already. You don't need to go to reduced or echelon form. Why is that?
Is it because it has infinitely many solutions?
No, no.
It doesn't have infinitely many solutions, but it doesn't have no solution.
We just removed that. I mean, I guess this would be infinitely many solutions if we had x4, right?
Yes, right.
Yeah, but we don't
Right.
have it.
Right. So the fact that you're now, of course, we can easily get a leading 1 in the third row, just divide by -4. So we're going to have leading 1s in all 3 columns. What does that mean?
We have
Sure.
what?
So it's clear that I can.
Oh.
It's clear that I'm going to be able to create this matrix. It's basically the 3 by 3 identity matrix with another row of zeros on the bottom.
Yeah.
So it's
I mean,
clear.
we can remove that, right? That row.
Which one?
The one row of like all zeros. We can just get rid of that, I guess, right?
No, you should leave that in the matrix.
Oh,
Don't just throw it away. But because it's important.
Okay.
But it's clear at this point that I can row reduce this. I can divide by -4. I'll get -1/2, and then well, if I want to know the actual scalars that I need to write the linear combination, I actually need to do the work. But my point is, you could say at this point, you know that there's not just an answer, there's only one answer. because you have leading ones in each column. Remember, you only have infinitely many solutions when there's a column with no leading one. So because all of the columns are going to have a leading one, and there's not no solution because you're not getting a contradiction on the bottom, you're going to have one unique solution.
Mm-hmm.
So at this point, your answer could just be yes. Now, if you went on and you found the linear combination and you wrote it out, then that's the best possible justification. But if you're rushed for time and you want to make sure you're answering every problem, you could stop here and say it's clear that the RF will have a leading one in every column, which means there's a unique solution. Therefore, the answer is yes. So you could do that.
So we're trying to see if the vector is a linear combination of these vectors. So if it has a unique solution, then it is a linear combination.
Yeah, because look at what we're solving. So what are we solving for? We're solving for x1, x2, and x3. Those are the scalars that produce the linear combination that gives you 0, 0, 0, 2. We just wrote it in matrix form, and then we know how to solve that system. But just keep in mind, we're solving for x1, x2, and x3.
The question just asks us if they exist, right? So we don't have to solve for them. If we know that it's solvable, we just say yeah.
But it does say justify your answer.
Oh, so you want to find them.
So what I'm saying is you can justify it without finding the actual linear combination, without actually finishing the solution.
Just explaining it?
Yeah, just explaining it. Now, of course, tell me what you got for your final, I won't go through the steps, but what did you get for your final?
X1, X2, X3.
Yeah, what'd you
7
get?
halves.
Negative 7 halves?
No, 7 halves.
7 half.
Okay, 7 halves.
And then
Negative
-1, and then -1
Negative
half.
1 half.
-1 and -1 half.
Mhm.
Okay. So if you got that far, then then you can say yes, and you can actually write it out. Yes, since. So if you didn't like all that business of explaining, then you could go all the way to reduced row echelon form. And that, if you did, and you're looking ahead to part E and know that you have to do it anyway, then maybe that's the best option in this case. Yeah, so at this point, you could say yes, since 0, 0, 0, 2 is equal to 7 halves times 1, 2, 3, 1 minus 1 times 2, 5, 7, 1 minus 1 half times 3, 4, 7, 1. You could actually write out the linear combination. Okay, so either way. Okay.
What would be the explanation if we didn't want to solve it? Would we just say since it has this matrix can be formed into RR like reduced row echelon format
Yeah.
as an answer?
Yeah. So we can say clearly when we don't have the time to go into too many details. I mean, it is clear at this point because you can certainly generate a leading one in the third column. So clearly, we will have leading ones in each column, which implies one solution. Therefore, yes. That would be the alternative. We will get but you have to, in order for that explanation to make sense to you, you have to see the equivalence between finding the scalars to create the linear combination and solving that corresponding, or putting that corresponding matrix in reduced row echelon form. Okay, moving on. Well, part E, we already did.
What was it? 1 second, let me bring it up again. I had a question if no one else has it. Oh yeah, let's answer part G, but then after that, can we jump to question number 3?
Sure.
Okay. Thank you.
So we got the RF, that's done. F, what's the rank? That's an easy one. What's the rank?
3.
3. We're going to have 3 leading ones. Rank A equals 3. Not asking for justification. G is just really testing whether you understand the concept of linear combination. How many vectors in R4 can be written as linear combinations of 1, 2, 3, 1, 2, 5, 7, 1, 3, 4, 7, 1? Now, since you just did part C and part D, which asked you for specific linear combinations that lead to those vectors, you might think there's some solving involved here, but there isn't. And it says explain how you know. So the answer to this one actually has nothing to do with the RREF. In fact, you could take this question completely in isolation without anything to do with what went beforehand and answer this question. What is a linear combination of those? Here's the point. What is a linear combination of those 3 vectors? So a linear combination is scalar times first vector plus scalar times second vector plus scalar times third vector. And where are those scalars? They're just real numbers. R, S, and T are real numbers. Now, and then you have to realize that when you do this, for whatever scalars you pick, when you multiply the scalars times the vector and then add everything together, what do you get? You get a single vector in R4. So how many of them can you make?
Infinitely many?
Infinitely many. And the only reason is that there's infinitely many real numbers. For every choice of R, S, and T, of which there are infinitely many, you're going to create a vector in R4. So it's like really reading the question carefully. How many vectors in R4? Well, we don't know what they'll be specifically, or whether we'll get all vectors in R4, but we know we'll have infinitely many of them for sure. Because we we have infinitely many choices for R, S, and T. A linear combination is that, R, S, and T are. So infinitely many vectors in R4. No, because see the difference is in up here when you get your RREF, we were solving, well, it's kind of backwards. We were taking a specific vector, actually going all the way back up to here. We took a specific vector in R4 and said, can we write that as a linear combination of those other three? And by going through this process, we found the one set of scalars that gives you that particular vector. See, that's a completely different question. I'm not sure. Is that making sense? Okay, I'm just, yeah. So now I'm not, it has nothing. I'm just saying, okay, if I take random linear combinations of those three vectors, how many vectors in R4 can I make? Well, infinitely many, because you can choose any scalars you want. Now, another question that would be a harder question to answer would be, can all vectors in R4 be written as a linear combination of those three? That's a harder question. Because yes, I know that there's infinitely many, but I don't know whether I get all the vectors. There could be infinitely many and still not have all vectors in R4. That's a question that we need a little couple more linear algebra concepts to answer easily. I mean, ultimately the answer is yes, because when you get that, when you reduce this this matrix to this, if you can get that shows that well, I don't want to complicate it with new definitions, but because of that matrix, we could answer that question eventually. Okay, so someone asked for 3. R2 to R2 is the orthogonal projection of R2 on the line 3/4 x. That is the projection, T of x is the projection of x onto L. Find a unit vector. So remember that, and if we're looking ahead down this question, the letter D says find the matrix of T. So what this problem is doing is kind of guiding you through the process of how to find that matrix. Now, there are 2 ways of finding the matrix. One is if you have the formula memorized. So when in class on Wednesday, I said, okay, these are the 4 matrices I want you to know. So if you know this one, you could do part D without doing parts B and C. Part B and C is guiding you through a different way of finding the matrix just by using the definition of projection, which is given. Okay, but let's go step by step. So we're talking about the line y equals 3/4 x, and it says find a unit vector parallel to L. This is the line L, with positive coordinates. So what do we need to do? So the first thing is you have to find a point, a vector on that line, which amounts to just finding a point on the line. So how do you find a point on the line? You just pick any point that satisfies the line. Pick a number for X and then find the Y. What's the easiest thing? Maybe. Are you guys still there?
Yeah.
Okay. So what should I pick for X?
1 or no, 2.
You could pick 1 or 2. Anything will work. I mean, I'd like to pick 4 just because it'll cancel the 4 and then I won't have any fractions. But those would certainly work. X equals 4 implies Y equals 3, implies the vector 4, 3. Notice it has positive coordinates, is parallel to L. Now, this is just a vector. This is a vector parallel to L. We need a unit vector parallel to L. So we have to go one more step and use the formula for that. So the unit vector, I use U for unit vector, is the vector divided by its magnitude. So remember the magnitude, that's the symbol for magnitude, is the square root of the sum of the squares. I'll just go down this way. So it's the square root of 4 squared plus 3 squared. Well, 4 squared plus 3 squared is 25. So the square root is just 5. So this is 4/3 divided by 5. Really, it means 4/3 times 1/5. So oops, that's not 4/3, that's 4/3. So it's 4/3 times 1/5. So the unit vector is 4/5, 3/5. Okay, is that making sense?
Yeah, so 4, 3 is the vector that's parallel to L, and 4/5, and and the final answer is the unit vector that's parallel to L.
Yes, that should have been a 5. Thank you. Yeah, that's so. Of course, once you have a vector on the line, like 4, 3, it's parallel to the line, or you could just think of it as being on the line. Then any scalar multiple will also be on the line. When we multiply it by 1/5, it's still going to be on the line, but now it's going to have a magnitude of 1. Notice if you square those now, you have 16/5 plus 9/5 is 25/5, which is 1. The square root is 1. Now, why is getting a unit vector important? Well, it's important for part B because part B gives you a formula that involves the vector u. But now I want to show you something. I actually want to jump to D and show you how you can do D very easily if you memorize the formula. It asks you for the matrix of T. So part D is usually we call it A. I mean, we don't have to call it anything, I guess. Just write it. So the formula was U1 squared, U1, U2. Oops. U1 squared, U1, U2, U1, U2, U2 squared. That's the formula for the matrix of an orthogonal projection, but you have to have a U, which is a unit vector. So the 4/5 becomes the U1, the 3/5 becomes the U2, and then we just plug everything in. So 4/5 squared is 16/25. U1, U2 is 12/25. Notice these are the same. So this one's always looking for shortcuts in how I think. And then 3/5 squared is 9/25. So that's your matrix. So if you need to find the matrix of an orthogonal projection, all you need to do is find a vector on the line, divide by its magnitude to get a unit vector, and then if you have the formula memorized, just plug in. Now, the other way of finding the matrix of a transformation, the definition way, not memorizing the formula, but just the definition, is to find the image or the output of the projection, the standard basis vectors subject to the given transformation. So let's go to part B. Part B says, find T of E1 equals the projection onto L of E1. Okay, so here you have to remember what E1 is. E1, if we're in R2, is this first standard basis vector 1, 0. Now I'm going to go right to the formula that's written in the parentheses where it says recall the projection of X onto L is X dot U times U, where U is a unit vector parallel to L. Okay, so the X in this case is this 1, 0.
Professor, may I see the A part of 3? If you are,
Yeah.
have you moved on to the 4 or?
No, so I did the A part of 3. The answer was this one, 4/5, 3/5. And then I jumped from part A to part D to show you how you can find the matrix of the transformation if you just have the formula memorized. You take your unit vector and plug it in.
Mm-hmm.
So notice it says for part D, it says find the matrix of T. You can use the formula, which we just did, or part B of this problem. So I'm going through now how to do part B. So it's saying find the projection. So we're going to use the formula. The formula is X dot U times U. So the X is 1, 0. We use the U that we got in part A, 4/5, 3/5. So we take the dot product and then multiply that dot product times U, which again is 4/5, 3/5. I'm missing something there. Okay, so 1, 0 dot 4/5 is just 4/5. Well, 1, 0 dot 4/5, 3/5 is just 4/5. So 4/5 times 4/5, 3/5 is 16/5, 12/5. I'm sorry, 25ths. Keep noticing this. 16/25 and 12/25. So that's T of E1. Now notice the definition of the matrix of a transformation says that the columns of that matrix are the images of the standard basis vectors. So notice how up here in this matrix that we already found by having the formula memorized, the first column was 16/25 and 12/25. That really comes from here. It comes because it's that, because that's the image of the first standard basis vector. So if you didn't have the formula memorized, once you get to here, you would say, oh, now that's going to be the first column of my matrix. T of E2 is going to be the second column of my matrix. So you have to remember E2 is 0, 1. So now I'm plugging in, now I have 0, 1 dotted with 4/5, 3/5. Oops. And then again, times U, 4/5, 3/5. And again, now this is just 3/5. That dot product gives me 3/5. That's 3/5 times 4/5, 3/5. And that's going to be 12 25ths and 9 25ths. And notice up here, that's the second column of my matrix. So once I do part B, I know if I remember the definition of a linear, of the matrix of a transformation being the image, the columns are the images of the standard basis vectors. Then once I find them, I just arrange them in columns and I have my matrix. So, okay, anyway, part C, it's just, I just wanted to see, this is a question I asked on one of, this is an old test question. I just wanted to see if people could actually knew what the orthogonal projection looked like. So let's see, what does it say here? Straighten out.
Is it part C now? That you're
Yes.
doing?
Now we're doing part C. Okay, so we have this line here, something like that. And we have a 1 here and a 1 here, something like that. It says use the graph on the left below to sketch E1 and T of E1. Okay, so E1 is just 1, 0. So going back to see if I can get this. Oh no.
You might have to move the page.
What do you mean move it?
We can only see the equation on the top, not the graph.
I know it's because my I'm getting this low system resource.
Oh.
That and see the voice. I don't know. It may crash. I don't know. Yeah. Okay. Yeah, everything froze. Can you still hear me?
We can't hear you, yeah.
Can, okay. This is the same problem I had before. I don't know I guess it's just bad internet. Oh, it says try. Maybe I should close. Let's see. Sorry, I'm trying to find a way out of this, but it just
It's okay.
it's just frozen. don't know what to do. Any
Oh, if it's frozen, can you try Control Alt and Delete? Just push
Yeah,
all at
that's
the
what
same time.
yeah, that's what
The,
the first thing I
oh, it didn't work.
and it just well yeah, it takes me to the where where you can lock the screen or sign out or
Can you open
maybe the
Task Manager?
task manager. Let's see if we can get the task manager and close some other stuff.
If it's the OneNote that's giving you the problem. Also, you can close the Chrome as well because we don't use that anymore, but
Yeah, so that maybe that'll help.
Microsoft Teams, if you're not using it, close that too. Just you could
What
press
about
Chrome and say and task. Just press on it
or just
if you're not using it though. Just click on it one time and task.
yeah, that's what I'm doing, but
That's
it's
weird.
not giving me
Or right click it, yeah.
Yeah.
there we go.
Okay, that's Microsoft Teams.
Oh, there we go.
You might have to do the same with Microsoft OneNote and open it again if it's not working.
Let's see if that helped. Oh yeah, that helped.
Okay, okay.
Okay. There we go. All right. Okay, so what are we doing here? Oh, yeah, I wanted to graph
E1,
Oh.
TE1, E1, E2, yeah.
yeah. So I'm gonna go grab color. So E1, is just this one.
Yeah.
Goes 1, 0. So there's your E1. And then T of E1. So T of E1 was
1625, 1225.
1625, yeah, 1225. So 1625 is, it's bigger than a half, a little bigger than a half, and 1225 is a little less than a half. So it's actually, so here's how we can, this is really what I wanted to see, is that the projection, here's E1. So from the tip of E1, I want to go to the line and make a right angle. This is y equals 3/4 x. I just wanted to see if people knew what a projection was in terms of like shadow. So this is how you draw it. You go from the tip of E1 to the line, and then the projection is the portion of the line that goes to that point. That's the projection.
Uh, okay.
That's T of E1. And it looks about right based on the scale. I mean, E1 is the x coordinate is a little bit bigger than 1/2, and the y coordinate might be a little less than 1/2. It's not perfect, but that's the idea. Just to see if you know that. And then the other one, let's just get another color, and so E2 is here. Oops, should go the other way. Oh, darn. Here. So there's E2. And then again, T of E2, I'd want to draw from the tip of E2 down to the line, and that should be T of E2. Oh, so let me move this one. This is T of E1, the orange one, and then this other one right here, I'll do that one in green. That will be that's T of E2. So you can see how this transformation is projecting both of those standard basis vectors onto the line.
Yep.
Okay.
Mm-hmm.
All right. So let's see.
Part E.
So you're okay with the second? Oh wait, I guess I did everything on the
You
same.
did everything except E, yeah.
I didn't follow the directions. Okay, so it got a little cluttered. That's why I did two separate graphs, but you get the idea. Part E. Okay, so part E was let S be the rotation of 180 degrees. I should have said counterclockwise about the origin, but I guess it wouldn't matter. Find the matrix of S and then find the matrix of S composed with T. So this is, we just finished that either Monday or Wednesday, finding the matrix of a composition. So basically it's taking the matrix of each transformation individually and then multiplying them together. That's how you get the answer to this one. But first you need to find the matrix of S. So here's where you need to remember this other formula. The matrix of a rotation, cosine theta, sine theta, minus sine theta, cosine theta. But our theta is pi, 180 degrees. So we want cosine pi. So for theta equal pi, so cosine pi is -1, sine pi is 0, minus sine pi is 0, and cosine of pi is 1. So that's the matrix of S. Now, what's the matrix of S composed with T? So if we call,
Professor,
Uh-huh.
isn't cosine of pi -1 in both cases?
Oh yeah, that's yes. I was thinking there. Yes, thank you.
You're
Yes.
welcome.
Okay, so this was our matrix of the transformation. So let's write, so if we call that one A, let's call that one A. And if we call this one B, what order do we multiply them in to get S composed with T? We want the matrix of S composed with T.
So you have T inside S technically?
Yes, yes. So if we were to put an argument here like S composed with T of X, that would be S of T of X. So T is going to act on the matrix first. So we want the matrix of T on the right side.
Mm-hmm.
So the matrix of S composed with T will be, if we call them B and A, would be BA like this, so that the matrix of T is on the right. Does that make sense why that is?
So T is A in this case?
The matrix of T is A. Yeah, so I just quickly labeled it like that, just so that we could refer to them easily. So that one was, I think it was 16/25, 12/25, 12/25, and 9/25. So now we just need to do that multiplication, and we get, what do we get? Negative 16/25 and negative 12/25. No, it just makes everything negative. Minus 12/25 and minus 9/25. Okay. So how are we doing? Oh, wow, it's almost 1.
Good.
You guys are doing good. You're hanging in there. Good.
Professor,
Uh-huh.
do you think you could go over 2C?
2C, sure. Yeah, I mean, we're pretty close to finishing everything. I think to do 2C, we're going to have to do 2B. I think we're going to have to do all 3 parts to do 2C. So first of all, the matrix, since T of X is equal to A of X, and because of the way the transformation is written out, this is going from R3 to R3, we're just going to grab the coefficients from the matrix, or from the rule.
Professor, I have a meeting, another meeting, so I have to leave, but I would like to know the answers for this one. So can you maybe post the answers?
Sure. Yeah, I
Just
can-
maybe print out the same sheet in OneNote that you're doing it as a PDF file and post it to Canvas. That would be good.
Yeah. I can do that.
Yeah, thank you very much.
Yeah, no problem.
Have a good day.
You too. Okay, so we have 1, 3, 2, 1, 4, 5, and 1, 2 minus 1. That's the answer to part A. For B, now we have to do RREF. So 1, 3, 2, 1, 4, 5, 1, 2 minus 1. This one looks like this one should come out pretty quickly. So let's multiply by -1 and add 0, 1, 3. Same thing, 0, -1 and -3. That's nice because the third row is going to go away. We add the second row to the third row and we just get 1, 3, 2, 0, 1, 3, 0, 0, 0. And now we need to just do one more step to get RF. We're going to multiply the second row by -3 and add it to the first row. So we get 1, 0, and then -9 plus 2 is -7. And then 0, 1, 3, 0, 0, 0. And that's RF. So that's the answer to part B. And then part C, using A, find all solutions to the equation AX equals 0. So we're assuming now that what we're doing essentially is we're taking the output of that transformation, turning it into equations where they're all equal to 0. And well, what do? We put it in, this is the first thing we learned how to do with matrices, is to solve. So the RF is, we have the RF, and you just have to, there's the understanding that there's another column of zeros now. If we're once we start thinking of it as a homogeneous system of equations, because now it's AX equals 0. Now we don't need to write those. Those will be completely unaffected by any row operations. They're all 0, so they can't be affected. So what we do is the thing where we identify what's the free variable. We look for the column that has no leading ones, which is the third column. So notice the first column has a leading 1, the second column has a leading 1, the third column does not have a leading 1. So that means x3 is a free variable. So with that in mind, we write out the systems of equation, the equations. So the first row is saying x1 minus 7x3 equals 0, because we're assuming it's homogeneous. Second row says x2 plus 3x3 equals 0. And now we want to write that in column vector form. Oops. So we're going from R3 to R3. So we're going to have 3 variables. And what are they? Well, the first equation says that x1 is equal to 7x3. The second equation, oops, it says that x1 is equal to 7x3. Second equation says that x2 is equal to minus 3x3. So minus 3x3. And then what's x3?
X3.
X3 is x3, right? Good. The free variable is always just itself. So that's it. Therefore, now when we were practicing this, we were replacing the free variable with some parameter like r. So therefore, let's see. The solutions are 7r minus 3r and r for r, any real number r.
What if we forget to say the scope of just in general things? Because I would normally forget to write R for all real numbers. I'll try not to, but
Yeah, I mean, it's one of those things. It's small, but it is important just because if I look at 7r minus 3r, I want it to be clear from what you're writing that you realize it's infinitely many solutions and what they are. It's not just a single vector. I don't think you would think that, but maybe it wouldn't be clear to you. It's when you say for R in R, that's what makes it infinitely many solutions. And it's not just any infinitely many solutions. You're telling me what they are. So it's a small thing. I mean, what would I take off if you didn't put that? I don't know, half of a point or something. I don't know. So just try to remember it. It's not a huge issue.
yeah.
Okay, anyway, is A invertible? So that's we kind of threw in this other question from the last section. Is A invertible? Now, this actually comes from section 2.4, so it probably wouldn't be a legit question since I said the only thing I would ask from 2.4 was finding the inverse of a matrix. But see if you can answer it. You might not remember it now, but we had this theorem that we did on Wednesday that said that a matrix is invertible. One of the equivalents, an equivalence to the matrix being invertible, is that its reduced row echelon form is the identity. So you can see here, because the reduced row echelon form is not the identity, that means it's not invertible. So the answer to D is no, since the R ref of A is not equal to the identity. That's just an easy way of saying it.
Can we also say no because the determinant is 0?
You could, but how would you know that? I mean, do you know the formula for the determinant of a 3x3 matrix?
Yeah.
Okay. If you know that and you could show that, then that's fine.
Okay.
That's true. I mean, that's actually something we haven't gone over yet, but like I said, I'm not going to ask you this question on this test because I kind of ruled it out as a possibility. But yes, you're absolutely right. You're adding some other information into this that we're already doing. Did we do everything? I think we did everything. Any other questions?
These are the main topics that will be, of course, like how far would you deviate from these kinds of questions on the test? Maybe different proofs, but like
that's a hard question
yeah,
because the reason it's a hard question is because a very slight deviation to me could be a major deviation to you.
mm-hmm.
So from my perspective, I would answer that question saying I would only have slight deviations from this. But you'll have to tell me after you see the test whether they're whether you think they, a lot bigger deviations. I think if you listen, I've given some hints in class and today, and if you listen carefully to those, made notes of those would be helpful. I've mentioned a couple of problems that I was considering as possible test questions. I did follow through on those hints. Oh, it's crashing again. Well, I guess that's probably a good time to sign out. Any questions before I close it down?
Oh, are you gonna upload this recording?
I don't know. I don't know if I can or if it's complete because of all the crashing. So I'll have to see what condition it's in or whether I get it. Oh, good. It's
Okay.
still a lot of people there. So, and anything else I can answer? There's still quite a few people here. Wow, good for you. I mean, I think I'm hopeful that if you can do this review, I'm really hopeful that you'll do well on the test on Monday. I really am. I don't think there's that much deviation, but if you want to yell at me on Monday and tell me that there was, okay, that'll be good feedback for me. But I don't think there is. I think you're going to do really well. If you can go through this review confidently, get the right answers, I think you're going to do very well on this test. And also pay attention to the points. I mentioned this earlier, but the bulk of the points are in the first three computational problems. So, you know, the proofs, save those for last. I mean, even if you don't do any of the proofs, you could still get 80% on the test. But I think you're going to do well on the proofs too.
Thanks so much. Very helpful today.
All right, you're very welcome. Well, I'll try to. I'm going to let my computer cool down a little bit, and then I'll write up the solutions a little bit later, and I'll at least post the solutions. I don't know what's going to happen with the video.
Okay. Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
You're